In April 2024, the River Deal Bridge, an essential crossing over the River Deal in County Limerick, Ireland, was successfully reinstalled after extensive renovation. The bridge, which serves as a critical link for local communities, had undergone significant structural wear over the years, necessitating a comprehensive refurbishment to ensure safety and longevity. The bridge replacement project was part of a broader infrastructure initiative led by the Limerick City and County Council to maintain and improve GE transportation routes across the county. Planning for the reinstallation began months prior, with engineers and planners coordinating closely to minimize disruptions. The old structure was carefully dismantled, and the new bridge was designed with modern materials and reinforced construction techniques to withstand both heavy traffic and natural elements like floods, which have been increasingly common in the area. During the reinstallation, traffic was rerouted to avoid congestion, and the council kept the public informed about detours and timelines, ensuring smooth transit for commuters and local businesses. Local residents, who had been anticipating the reinstallation, expressed relief as the bridge reopened, as it restored convenient access to nearby towns and facilities. The Killaloe Bridge Lift project, completed in April 2024, marked a significant milestone for infrastructure and transport in County Clare and County Tipperary, Ireland. This long-awaited improvement to the historic Killaloe Bridge, a key crossing over the River Shannon, has greatly enhanced the connectivity between the towns of Killaloe in County Clare and Ballina in County Tipperary. The project, executed with sensitivity to the bridge's heritage and environmental context, introduced a modern lift system that aids in reducing traffic congestion, improving accessibility, and preserving the structural integrity of the bridge, which dates back to the 18th century. Prior to the lift installation, Killaloe Bridge was a bottleneck for vehicular and pedestrian traffic, creating frequent delays in the area and presenting accessibility challenges for elderly residents and those with mobility issues. The lift system now allows traffic to flow more smoothly by providing a controlled, efficient way for vehicles to cross during peak hours, alleviating traffic on the narrow 13-arched bridge. Additionally, the installation aligns with Ireland's sustainability goals by promoting active transportation modes, encouraging more people to walk or cycle across the bridge without causing congestion. The completion of the bridge lift was the result of collaborative efforts between local authorities, transportation agencies, and community stakeholders, all of whom sought to preserve the historical essence of the bridge while upgrading it to meet modern needs. The construction of the new Oliphants River Arch Bridge by Stefano T. Stock Civils is a significant infrastructure project undertaken to improve capacity and safety along National Road 7, N7, Section 4 in South Africa. This new bridge, located within the West Coast District Municipality of the Western Cape Province, represents an essential upgrade to the existing infrastructure due to the structural limitations of the original bridge, which was built in the 1970s primarily for railway use. Over time, the old bridge suffered from structural degradation, including notable cracks, which prompted SANRAL, South African National Roads Agency Society Limited, to commission a safer and more durable solution rather than a mere expansion of the existing bridge. To address these needs, SANRAL enlisted a collaboration between Rendell and Ingerup, South Africa, which undertook an in-depth peer review of the design for the new Oliphants River Bridge. Oricon, a prominent South African engineering firm, designed the bridge, emphasizing both strength and safety. The new bridge, with a total length of 168 meters, includes a main arch spanning 96.6 meters over the river. On each side of this main arch, smaller spans connect to the northern and southern approaches, with 3 spans of 14.6 meters on the north and 2 spans of 13.8 meters on the south. The structural design of the bridge includes a split arch feature, with 2 ribs beneath the deck connected by beams at each pier, forming a ladder-like structure that reinforces stability. These twin-column piers are integral to the arch itself, incorporating concrete hinges near the deck for enhanced flexibility and load distribution. The deck design features a continuous reinforced concrete slab with diaphragm beams at each pier for added structural cohesion. Designed to accommodate modern traffic needs, the bridge is 12.25 meters wide, providing 2 lanes, each 3.7 meters wide, 1.0 meter wide shoulders, and a 1.5 meter wide sidewalk for pedestrian safety. Precast concrete F-shaped parapets, each 1.1 meters high, will enhance safety along the bridge's edges. The bridge is anchored on shallow rock foundations, ensuring stability and resilience. Grendel and Ingerop, South Africa's contributions extended beyond design verification to include rigorous geotechnical assessments and structural analysis, which guided the project to meet high standards of durability and functionality. By replacing the old bridge with this modern arch bridge, the project not only resolves existing structural concerns, but also significantly enhances road user safety and capacity, supporting the long-term infrastructural needs of the N7 corridor. The Senku River Road Bridge is a remarkable feat of civil engineering, demonstrating the effective use of steel composite design to achieve both functionality and durability. This bridge, spanning a total length of 142 meters and a width of 11 meters, was developed to enhance connectivity and improve transportation infrastructure across the Senku River. The bridge is composed primarily of a steel composite structure, which combines steel girders with a reinforced concrete deck to deliver an optimal balance of strength, resilience, and cost-effectiveness. In this design, steel girders serve as the primary load-bearing components. Steel's high tensile strength makes it ideal for supporting the bridge's weight and the loads exerted by vehicular traffic. Meanwhile, the concrete deck provides a durable and stable roadway surface that distributes loads effectively across the bridge's width and supports the underlying girders. The bridge is supported by 2 abutments and 3 piers, creating a stable foundation and distributing the bridge's load across multiple points. The abutments are located at each end of the bridge, anchoring the structure to the riverbanks and bearing the horizontal forces that may arise from environmental stressors such as wind and water flow. The 3 piers, strategically positioned along the length of the bridge, further distribute the weight and provide additional support to the central span. These piers are built to withstand both the dynamic loads from traffic as well as environmental pressures, seasonal changes in river levels. From a structural engineering perspective, the steel composite approach used in the Senku River Road Bridge is advantageous because it integrates the strengths of both steel and concrete while mitigating their respective weaknesses. Steel, though strong under tension, can be vulnerable to buckling when subjected to compression, especially over extended spans. Concrete, on the other hand, is highly resistant to compression but lacks tensile strength. By combining these materials, engineers create a bridge that performs well under both compression and tension, enhancing its lifespan and minimizing maintenance needs. The bridge's dimensions, a span of 142 meters and width of 11 meters, indicate that it can comfortably handle both vehicular and pedestrian traffic, making it a vital infrastructure component for the region. The wide deck allows for multiple lanes, increasing traffic flow efficiency and safety. Additionally, the structural durability ensures that the bridge can serve the community for many years, accommodating both present and future transportation needs. The North Terrace and King William Road intersection in Adelaide, a vital juncture for the city's transport network, has recently undergone significant upgrades to enhance safety, efficiency, and accessibility. As a major intersection connecting key points in Adelaide's cultural and commercial heart, including landmarks like the Adelaide Railway Station, Parliament House, and the Adelaide Festival Centre, the intersection serves a high volume of pedestrians, vehicles, and public transportation, especially the city's tram network. The upgrade works, part of a broader investment in Adelaide's transport infrastructure, have focused on modernizing traffic signal systems, improving pedestrian crossings, and creating dedicated bike lanes. These improvements aim to reduce congestion, prevent traffic bottlenecks, and ensure smoother movement across the intersection for all road users. Improved pedestrian facilities, widened crosswalks, and raised curbs have been added to enhance safety and accessibility, especially for those with mobility issues. A key component of the project involved upgrading the tram tracks and realigning tram stops for more seamless access. The tram system is an integral part of the city's public transport network, and these updates are expected to reduce delays, improving service reliability. Additionally, updated traffic light coordination aims to minimize wait times and prioritize public transport, helping to keep trams and buses on schedule. During construction, several temporary traffic diversions and lane closures were implemented, which required extensive planning to mitigate disruption. Comprehensive communication with the public, along with clear signage, was crucial in helping commuters navigate the changes.
The installation project at JR Sasagori Station marks a significant endeavor in the realm of construction and engineering, centering around the creation of a pedestrian walkway facilitated by the utilization of the Liebherr LTM 11200NX, an awe-inspiring 1,200-ton all-terrain crane. This project not only underscores the remarkable fusion of advanced technology and precise execution, but also highlights the intricacies involved in erecting bridge girders that will gracefully span the bustling railway tracks. At its core, the project embodies a convergence of innovation and necessity, driven by the imperative to enhance accessibility and safety for pedestrians navigating the station area. The undertaking unfolds in multiple phases, each characterized by meticulous planning and seamless collaboration among various stakeholders, including engineers, construction workers, and project managers. The heart of this project lies in the deployment of the Liebherr LTM 11200NX, an engineering marvel that showcases the pinnacle of heavy lifting machinery. This behemoth of a crane combines remarkable lifting capacity with exceptional mobility, making it an ideal choice for tasks requiring the precise placement of large and heavy components. The crane's hydraulic jib extends to dizzying heights, enabling it to effortlessly reach over the expanse of the railway tracks, and its all-terrain capabilities ensure it can navigate various ground conditions. The project's hallmark moment arrives as the bridge girders, meticulously fabricated off-site to exact specifications, are transported to the installation site. The crane's colossal lifting prowess is harnessed to hoist these gargantuan girders into position, gracefully spanning the railway tracks with an air of finesse that belies their massive weight. The girders are aligned with the utmost precision, reflecting not only the crane operator's skill, but also the advanced technologies that facilitate real-time adjustments. The assembly process is a delicate dance of engineering precision and human expertise. Operators work in tandem with the crane's cutting-edge control systems, ensuring that the girders are smoothly integrated into the evolving structure. Safety is paramount throughout this endeavor, with rigorous protocols in place to safeguard the workers, the crane operators, and the railway's integrity. As the final girders are set in place, the bridge's form begins to take shape, embodying the fruits of countless hours of planning, calculation, and labor. The successful erection of the bridge girders marks a triumphant milestone, demonstrating the fusion of innovation and skill required to accomplish intricate feats of modern engineering. In essence, the installation project at JR Sasagori Station is a testament to human ingenuity and technological prowess. It showcases not only the capabilities of the Liebherr LTM 11200NX crane, but also the collaborative efforts of various experts who come together to create a lasting infrastructure that will serve the community for generations to come. This project stands as a beacon of progress, illustrating how engineering excellence can shape the world around us. The construction process began with the establishment of the bridge's foundations and supports. Work commenced on the south abutment and north retaining walls, essential components that provided stability and anchored the bridge to the terrain. Careful formwork was installed during the construction of the south abutment, ensuring precise shaping and molding of the concrete structure. Next, the retaining wall and girder launch phase commenced, which involved placing and positioning the girders that would eventually support the bridge deck. This step required meticulous planning and execution to ensure the structural integrity of the bridge. Attention then turned to the installation of the stainless steel deck reinforcing. This crucial step reinforced the bridge deck, enhancing its load-bearing capacity and ensuring its durability over time. The deck screed test runs followed, during which the bridge deck surface was carefully leveled and smoothed to achieve a uniform and even finish. To protect and enhance the concrete curing process, insulated tarps were placed over the deck, providing a controlled environment for the concrete to set properly. Curing is vital for the long-term strength and resilience of the structure. Once the deck was fully cured, the placement of approach slabs and the pier deck section took place. These components allowed for the smooth transition of vehicles onto and off the bridge, ensuring a safe and efficient traffic flow. Finally, parapet forms and reinforcing were installed to create the bridge's protective barriers and ensure the safety of motorists during their journey across the newly constructed Sombrio Bridge. The construction of the Sombrio Bridge marked a significant infrastructure upgrade on Highway 14, situated near Port Renfrew. The project aimed to replace the existing single-lane timber bridge with a modern, eye-catching two-lane structure that spanned 124 meters, combining concrete and steel in its construction. The endeavor also involved creating a new 1.2-kilometer highway alignment, designed to meet a 70 km/h standard with 3.6-meter wide lanes and 1.5 meters of paved shoulders. Additionally, the bridge approaches were realigned and paved, and a 5.4-kilometer stretch of the highway leading east from Sombrio to Lines Creek underwent resurfacing. The construction of a wider Shepherd Bridge marks a significant milestone in enhancing the safety and convenience of the city's cyclists and pedestrians. Currently, the bridge's shared use between thousands of trucks and cyclists has proven to be a less than ideal arrangement for both parties. The plan involves widening the bridge over the Maribyrnong River from its existing 4 lanes to a more accommodating 6 lanes. This expansion not only ensures smoother traffic flow for vehicles, but also paves the way for the construction of a separate, dedicated cycling and walking bridge alongside it. The importance of this improvement cannot be overstated, as Shepherd Bridge serves as a crucial route connecting the inner west to the city center. Presently, cyclists are forced to navigate a narrow path in close proximity to a busy road filled with heavy trucks, posing significant safety risks. With the addition of a purpose-built cycling and walking bridge, cyclists can finally enjoy a safer and more enjoyable commute. The separated pathway will shield them from vehicular traffic, reducing the likelihood of accidents and promoting a healthier mode of transportation. As part of the ambitious project to electrify the Midland Main Line, several structures along the route need to be reconstructed to accommodate the installation of 25,000-volt overhead line equipment for safe and efficient rail electrification. One such structure that required attention was Ford End Road Bridge, located to the south of Bedford Central Station. The bridge, a 19-span brick arch, served as a vital crossing over the Midland Main Line, but its third span from the west lacked sufficient clearance for the electrification equipment to pass safely beneath. Engineers and construction teams decided that the third span from the west had to be carefully removed and replaced with a modern bridge deck made of precast concrete units. The reconstruction involved a series of carefully orchestrated steps to ensure a seamless transformation while preserving the historic significance of the existing structure. Demolition of the third span called for sensitive monitoring equipment and truck protection to be employed. These measures were crucial to prevent any damage to the rest of the bridge during the removal process. With utmost care and precision, the outdated section was dismantled, making way for the installation of a more suitable and contemporary design. After the successful removal of the old span, the new bridge deck made of precast concrete units was skillfully positioned in place. Advanced cranes were utilized to lift and secure the components, ensuring the structural integrity and safety of the reconstruction. The replacement deck was engineered to meet the modern requirements for electrification clearance and overall bridge stability. As the project nears its completion, the Ford End Road Bridge is taking on a renewed appearance, combining the sturdiness of modern construction with the timeless charm of its brick arches. Following the installation of the new deck, the focus shifted to the parapets of the bridge. The parapets are essential for providing safety and protection to pedestrians and vehicles using the crossing. New parapets were carefully craned into position, and their design and aesthetics were aligned with the existing structure. To maintain the architectural harmony of the bridge, the parapets were refaced in brick, seamlessly blending them with the rest of the historical facade. In 2016, the Arcola High Bridge Rail Replacement Project took place over the scenic St. Croix River in Somerset, Wisconsin. Spanning an impressive 2,682 feet in length and towering 184 feet above the river, the bridge held a rich history as it had served the community for over a century. The primary objective of this significant endeavor was to replace the aging railings on the bridge, ensuring the safety and structural integrity of this iconic landmark. The existing railings, being over a century old, were no longer able to meet modern safety standards, posing a potential risk to pedestrians and vehicles passing through. Considering the bridge's historical significance and the delicate ecosystem surrounding the St. Croix River, engineers and construction crews collaborated to install new, durable railings that complemented the bridge's architectural heritage while enhancing its safety features for years to come. The completed quantity of concrete works reached 39,582 cubic meters, representing an impressive 81.08% of the total required amount. This substantial achievement showcases the construction team's efficiency and dedication. Additionally, the steel works for Section 1 were fully completed, with a total quantity of 13,214 tons, ensuring the structural integrity and strength of the project. The concrete works for this section were fully completed, with a total quantity of 27,647 cubic meters. This accomplishment demonstrates the successful execution of concrete pouring, ensuring the foundations and structures are in place. In terms of steelworks, 10,974 tons were completed, which accounted for 53.96% of the required amount. While there is still work to be done, the completion of over half of the necessary steel works is a notable achievement for Section 2 of Kanwannerski Island within the Petersburg Western High-Speed Diameter Project. Kanwannerski Island, Section 3, demonstrated remarkable progress in both concrete and steel works. The completion of 51,525 cubic meters of concrete represented a significant milestone, reaching 87.82% of the total required amount. Moreover, the steelworks in Section 3 showed impressive advancement, with 16,851 tons completed, accounting for 85.58% of the required amount. Kanwannerski Island, Section 4, Concrete works. The completed quantity of concrete works for Section 4 was 34,273 cubic meters, accounting for 91.13% of the required amount. Steelworks. The steelworks for this section amounted to 2,572 tons, representing 45.26% of the required amount. The Berg River Bridge, a remarkable engineering feat situated within the picturesque Val d'Avia estate, stands as a testament to human progress and connectivity. Officially inaugurated on June 21, 2018, by the Executive Mayor of Drakenstein Municipality, Councillor Conrad Poole, the bridge has since become an iconic link connecting communities and enhancing accessibility. Martin Venter, the visionary founder and CEO of Val d'Avia Estate, expressed his pride during the opening event. highlighting the symbolic significance of bridge construction as a representation of human advancement. He emphasized the bridge's role in benefiting not only the estate's residents, but also the wider community. Stretching over the tranquil waters of the Berg River, the bridge forms a vital link between the Valdivia estate and the R45 Simondium Road. This connection, established through the newly built Berg River Gatehouse, has significantly reduced travel times to key destinations. Commuters now enjoy a mere 30-minute journey to the Cape Town International Airport and the city itself, a 16-minute drive to Stellenbosch, and a mere 3 minutes to Paarl Main Road. Notable for its impressive scale and significance, the Berg River Bridge holds several intriguing facts. It proudly holds the distinction of being South Africa's first private bridge of such magnitude. With a length spanning an impressive 400 meters, flanked by roads on both sides totaling 1.2 kilometers, the bridge creates an essential conduit for efficient travel and transportation. The construction process of the Berg River Bridge was a monumental endeavor that spanned 2 years, culminating in its completion. The project required a substantial investment of approximately R100 million, reflecting the significance of this undertaking in terms of both engineering and community development. The construction process of the Berg River Bridge was a monumental endeavor that spanned 2 years, culminating in its completion. The project required a substantial investment of approximately R100 million, reflecting the significance of this undertaking in terms of both engineering and community development.
The Rosbrick Bridge, a vital transportation link connecting Moorsbach and Rosbrick, has undergone a remarkable transformation, culminating in its reopening after 7 months of extensive reconstruction. The bridge's history dates back to 1948, and its significance lay not only in its role as a roadway, but also as a structure spanning over crucial railway tracks, including the prominent Frankfurt-Paris line. The endeavor to rejuvenate the bridge was driven by necessity. Over the years, the bridge had deteriorated to a point where the specter of collapse loomed large. The risk was too significant to ignore, prompting authorities to embark on a massive project that demanded both financial investment and engineering expertise. The initiative, financed entirely by the department, amounted to a substantial sum of 4.7 million euros. This investment was not just for repairing the bridge, but entailed a comprehensive approach. The old, weakened structure was completely dismantled, paving the way for a new and robust incarnation. The renovation process unfolded in several phases, each carefully orchestrated to ensure a smooth transition and minimal disruption to the daily lives of commuters. Prior to the commencement of construction, traffic management strategies were implemented, beginning with restrictions on vehicles weighing over 3.5 tons. This was followed by alternating traffic for cars and vans once preparatory work commenced. A pivotal juncture in the reconstruction journey arrived during the Pentecost weekend. In an astounding feat of engineering prowess, a 72-hour race against time unfolded beneath the bridge. The railway line passing underneath, a part of the SNCF network, required a complete shutdown. Tracks and overhead wires were disassembled, allowing for the removal of the bridge's 1,400-ton concrete deck. This high-stakes operation was executed flawlessly, a testament to the skill and precision of those involved. The collaboration between various stakeholders was evident in the seamless execution of this intricate plan. The bridge was dismantled and relocated, making way for its eventual replacement. Train traffic was temporarily halted to facilitate the installation of the new deck, a process that spanned several weeks. Amidst the disruptions and challenges, the local community demonstrated resilience and adaptability. The road closure between Rosbrick and Moorsbach had ramifications for local businesses. To address these economic impacts, local merchants and entrepreneurs united under the banner of an association named GEAR. This collective effort underscored the shared responsibility to mitigate the effects of the construction process on the region's economy. Finally, after months of construction, the Rossbrick Bridge emerged from its metamorphosis. On a Tuesday morning at 9:30 a.m., the president of the Departmental Council of Moselle inaugurated the new bridge. With the completion of final installations, including guardrails and safety rails, vehicular traffic was reinstated, heralding a return to normalcy for the communities it connects. The Rossbrick Bridge project stands as a testament to human ingenuity, determination, and collaboration. It encapsulates the dedication of those who worked tirelessly to ensure the safety and convenience of commuters while safeguarding vital transportation infrastructure. As vehicles once again traverse this route, they bear witness to the triumph of engineering and the resilience of a community united in the face of disruption. The Pemasangan box girder process begins with jacking down, where the box girder components are gradually lowered into their designated positions. This step requires careful precision to avoid any misalignment or damage during the lowering process. The jacking down procedure sets the foundation for the subsequent stages of assembly. Assembly is a critical step in Pemasangan box girder, involving the connection of individual box girder segments to form a continuous structure. The assembly process demands meticulous attention to detail to ensure that the segments align perfectly and that structural integrity is maintained throughout the length of the girder. Applying a primary coat of paint to the splices is essential for corrosion prevention and overall durability. This layer of paint acts as a protective barrier, safeguarding the girder against environmental factors that could compromise its structural integrity over time. The assembly push bar plays a pivotal role in ensuring the accurate alignment of box girder segments during the assembly process. This component assists in the controlled movement and positioning of the segments, minimizing the risk of misalignment. UD1, a specific component of the box girder, is brought to the construction site, marking an important milestone in the Pemasangan process. Its arrival signifies the transition from off-site fabrication to on-site construction. The installation of CHO, a crucial part of the box girder, is a meticulous task. Proper installation ensures that the box girder structure will bear loads effectively and safely. Roller guides are installed to facilitate the controlled movement of the girder during construction and maintenance. These guides help distribute the loads and forces encountered by the girder, allowing for smoother adjustments and positioning. Inspecting the cover splice ensures that the box girder's protective covering is in place, guarding against corrosion and damage. This inspection contributes to the long-term durability of the structure. The process of launching involves moving the assembled box girder a certain distance along the bridge's alignment. This staged approach allows for controlled progress and aligns with the construction schedule. Continuing the launching process, the box girder is moved to position P2 along box line E. This strategic movement corresponds to the overall bridge design and alignment. After the successful positioning of the box girder, the assembly push bar is dismantled. Its role in ensuring alignment is no longer needed at this stage. Temporary lifting towers are disassembled once their purpose of facilitating the lifting and lowering process is fulfilled. This step clears the construction area for further work. Rollers, which aided in the controlled movement of the girder, are removed as they are no longer required in the later stages of construction. UB3 components undergo pre-assembly to prepare them for integration into the box girder structure. Pre-assembly ensures that each part fits accurately and contributes to the girder's overall stability. UD1 is moved to its designated position and then slid into place, aligning with the box girder's overall configuration. Lowering down towers are installed to assist in the precise positioning of components, such as UD1, during the construction process. Bolts are inspected for proper installation and are tightened to the required torque values, ensuring secure connections between components. An additional coat of primary paint is applied to the splices, reinforcing the protective layer and enhancing the structure's resistance to corrosion. The jack-down process, similar to the initial jacking-up process, involves controlled lowering of components to achieve the desired alignment and connection. Component arrival on site, splice paint, shoe installation, remove lowering down tower, pre-assembly, slide to position. These steps mirror the earlier stages of the process involving the arrival, preparation, and integration of various components into the box girder structure. These steps are executed with the same precision and attention to detail as before.
Erection box girder segments are a fundamental component in the construction of bridges and viaducts. They form the superstructure of these structures, providing the platform for vehicles and pedestrians to traverse across bodies of water, valleys, and other obstacles. The design and construction of these segments require meticulous attention to detail, ensuring they can bear the intended loads while maintaining structural integrity over time. VSL Indonesia's approach to fabricating and installing erection box girder segments involves a combination of advanced engineering principles, cutting-edge materials, and state-of-the-art construction methods. The process begins with the design phase, where engineers collaborate to create a segment that meets the project's specific requirements in terms of dimensions, load-bearing capacity, and aesthetics. Computer-aided design, CAD, software, and simulation tools are employed to optimize the segment's performance and durability. Once the design is finalized, the fabrication process commences. High-strength concrete, reinforced with steel bars, is cast into molds to form the box girder segments. These segments are cured under controlled conditions to ensure their strength and durability. VSL Indonesia employs stringent quality control measures during fabrication to guarantee that each segment meets the highest standards of construction excellence. The installation of erection box girder segments is a remarkable feat of engineering precision. Large cranes or specialized launching gantries are employed to carefully position and lift the heavy segments into place. VSL's engineers ensure that the segments are aligned accurately and securely connected to adjacent segments, forming a seamless and robust superstructure. VSL Indonesia's expertise in erection box girder segments extends beyond mere construction. They contribute significantly to the advancement of infrastructure development in Indonesia and beyond. The TBM, an acronym for Tunnel Boring Machine, is an engineering marvel designed to excavate a 2.2-kilometer tunnel along the S19 expressway, connecting Rzeszów South to Babaca. The undertaking is an intricate process that involves the assembly of individual TBM components, subsequently followed by equipping them for their intended task. Concurrently, the construction of the southern portal is underway, involving geotechnical efforts that will pave the way for the TBM to make its first incision into the rock. The extraordinary journey of transporting the TBM's main shield, a colossal structure weighing 220 tons, measuring 15 meters in length and 9 meters in width, began with a feat of engineering in its own right. The shield was transported on two meticulously prepared platforms spanning an impressive 74 meters in length. This awe-inspiring endeavor necessitated exhaustive analysis to determine the optimal route. Collaborating with experts from Rzeszów University of Technology and Silesian University of Technology, a route was strategically mapped out. The voyage commenced with the TBM components arriving at Szczecin, one of Poland's largest ports, after being transported by sea from Santander, Spain. Here, the transition onto barges and pontoons was executed to navigate along the Oder River, a route that ultimately led to Opole. From Opole, the next phase of the journey unfolded through road transport, culminating at the construction site in Babaca. The logistics of this transport spectacle were mind-boggling. The combined weight of the TBM and its cargo approached a staggering 500 tons. To minimize disruptions stemming from necessary road closures, the movement of the TBM exclusively transpired during nighttime hours. This spectacle captivated the entire nation, with hundreds of local residents bearing witness to the awe-inspiring precision displayed by the transportation team. The intricacies of this operation showcased not only the machine's grandeur, but also the seamless orchestration of the entire endeavor. Opting for a route that ensured safety over brevity was a paramount consideration. Roads were carefully selected for their load-bearing capacities, guaranteeing the secure passage of this gargantuan machine. While the chosen route might not have been the shortest, it undoubtedly was the most prudent choice, accounting for both the TBM's enormity and the safety of the transportation process. By the end of January, a monumental achievement marked a pivotal moment in the construction of the S19 expressway in Poland. With remarkable precision and meticulous planning, all the components of the tunnel boring machine, TBM, had successfully arrived at the construction site in Babica, setting a new benchmark for Poland's transportation history. The successful transportation of the TBM from Spain to Poland marked an extraordinary milestone in the S19 expressway tunnel construction. This achievement resonated far beyond its technical implications, symbolizing the prowess of human ingenuity and collaborative expertise. As Poland observed this remarkable spectacle, it heralded a new era of infrastructure achievement,